Well, in this lesson we're going to focus on solving the homogeneous system. We're not going to find any particular solutions, but looking for how to solve a system of equations that's homogeneous. And believe it or not, it's going to be involved with some linear algebra topics called finding eigenvalues and eigenvectors of matrices.
Okay.
All right, so that's what we're about to do. So, we learned that the general solution of a homogeneous system is a linear combination of vectors that are solutions of the system. And in the system we looked at, we could notice that both of the linearly independent solutions are the form x sub I equals k1, k2, constant k1, k2, 1 and negative 4 in this case, and 1 and 1 in this case, times e to the lambda sub I t. So in e to the, in this case, lambda sub I was negative 3, in this case it was 2 for those particular constants. So if we make the supposition that any solution to a system where you have a derivative vector equal to an n by n matrix times a vector has the form, the solution would be a series of constants times e to the lambda t, and we could call that vector of constants vector k times e to the lambda t. If indeed it is a solution, then we know that x prime is equal to a times x. And so therefore x prime, and if we took the derivative of this, of course the derivative of e to the lambda t is lambda times e to the lambda t, so we get vector k times lambda e to the lambda t. And on the right side we would have a times k times e to the lambda t by differentiating x on this side and by multiplying that matrix A times our solution vector, this one, right? So differentiate it on this side, matrix A times it on this side. Now, what does that lead us to? If we divided both sides by e to the lambda t, so that part would all cancel out, we'd have just really that k lambda equals a times k. Or maybe we could write that a little differently. 0 equals a times k minus k times lambda, or lambda k, either way. So a minus lambda sub lambda times I times vector k equals 0. Now, that lambda times I, if we factored the k out of this, then we would have an identity matrix of the same size as A, but with the ones multiplied by lambda. So the only way to find a non-zero k would be to satisfy this, that would satisfy this equation would be if the matrix A minus lambda I was a singular matrix. Think about it. The only way this could be solved if k isn't 0 would be if A minus lambda I is singular. And that makes the determinant of A minus lambda I 0. So how do you find what's called the characteristic equation, an eigenvalue and eigenvector of a matrix? The equation A minus lambda I is 0 is called the characteristic equation of the system. There, got it. We got it from here. That's the characteristic equation of the system, and the solutions of that characteristic equation, lambda 1, lambda 2, dot, 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 up to lambda n, are called the eigenvalues of matrix A, and vectors k sub I associated with lambda I are called the eigenvectors of matrix A. Each eigenvector is associated with a different eigenvalue.
Can you get it?
So I hope you can. So sometimes you have distinct eigenvalues for the matrix.
Oh.
Yes, and that's kind of a nice thing. So if we have lambda 1, lambda 2 up to lambda n are distinct eigenvalues of an n by n matrix A, and k1, k2 up to kn are the associated eigenvectors. If we can do that, then the general solution of the equation x prime equals a times x is C1 times eigenvector K1 times e to the lambda 1 t plus C2 times vector K2 eigenvector K2 times e to the lambda 2 t. See, this K2 vector is associated with this eigenvalue, this eigenvector, this eigenvalue, all the way up to C sub n vector K sub n e to the lambda sub n t. As expected, it is an n parameter family of solutions. See, because there's exactly n constants. So, and of course, the sum of all these vectors is itself a vector, and that is the vector that is a solution to the system.